If you ever just stop and watch the world for a minute, you realize that motion is, well, it's everywhere. But it's almost never just a simple straight line, right? It's the graceful curve of a water fountain or the wild path of a bird getting tossed around by the wind. To really get a handle on how our world works, we need to understand this secret language of motion. So let's jump right in with what seems like a simple question. Take a look at this penguin here, launching itself out of the ocean. To get the farthest possible jump onto that ice, what angles should it take? Super steep? Really shallow? It's not just a random guess, you know? There is a single perfect answer, and we're going to figure it out. And this isn't just about penguins either. Think about it. How does a pilot point her airplane to land in Chicago when a massive crosswind is trying to blow her to St. Louis? Or how does a satellite stay perfectly in orbit without just flying off into space? Turns out the answers to all of these questions are all connected by one single, incredibly powerful idea. To crack these puzzles, we've got to upgrade our thinking. We need to move beyond just asking how fast or how far and start asking the really important question, in which direction? And this is it. This is the key that unlocks everything. It's a new language, the language of vectors. And I promise, once you start speaking it, you'll see the physics of the world in a completely new light. So, let's get started. And like with any new language, we have to start with the absolute basics. What in the world is a vector? Okay, so you're already an expert in something called scalars, even if you don't use that word. A scalar is just a number. Your speed on the highway, 100 kilometers per hour, that's a scalar. But a vector tells the whole story. It's not just 100 kilometers per hour. It's 100 kilometers per hour headed north. That direction part, that's the missing piece of the puzzle. And the cool thing is, working with them is actually pretty intuitive. I mean, adding vectors is basically just like following directions. If I said, hey, walk 3 blocks east and then take a left and walk 4 blocks north, you know exactly where you'd end up, right? That's vector addition. The shortcut from where you started to where you ended up, we call that the resultant. Now, to make all this work with, math, we use these handy little guides called unit vectors. Just think of them as pure direction, one for sideways and one for up and down. They let us break any complicated diagonal movement into 2 really simple steps. It's kind of like having a super simple GPS for any kind of motion. Okay, now that we've got the basic grammar down, let's put our new language to the test and finally tackle that airplane problem. Here's the absolute key. Velocity never exists in a vacuum. It's always relative to something else. Like if you're walking on a moving train, you have a certain speed relative to the train, but the train itself has a speed relative to the ground. To figure out your actual speed over the ground, you have to account for both. We call this your frame of reference. And this is how vectors make a really tricky problem, well, simple. The pilot knows the direction she wants to go. That's one vector. But the wind is pushing her sideways. That's another vector. By just adding those 2 vectors together, she knows exactly which way to point the nose of the plane, so the final path, the resultant, takes her right to her destination. It's actually pretty elegant. All right, we are armed with our new vector toolkit. Let's circle all the way back and finally solve the mysteries from the beginning, starting with our flying penguin, which is really about anything that gets thrown or launched through the air. Now, this is maybe the single most important idea in all of this, and it's kind of mind-blowing. Just watch these 2 balls. One's dropped straight down, the other is shot completely sideways. But look, they hit the ground at the exact same time. That's because gravity only pulls things down. It has 0 effect on an object's forward motion. The 2 are completely, totally separate. And because those 2 motions are independent, the path of any object flying through the air, whether it's a tiny drop of water, our penguin, or a home run baseball, follows a perfect, predictable arc. We call it a parabola. It's this beautiful shape you get from constant speed sideways and constant acceleration downwards. And yep, there's even a mathematical recipe that describes this perfect curve. Now, don't let the equation intimidate you. Just think of it as the blueprint, the code that nature uses to draw that arc for anything that gets thrown. So back to our penguin. Using that blueprint, what's the magic number? To get the absolute maximum horizontal distance, the launch angle has to be exactly 45 degrees. Not 44, not 46,
45 degrees is the perfect sweet spot that balances time in the air with forward speed. Mystery solved.
We have one last puzzle to put together. What about motion that isn't an arc? What about moving in a perfect circle, like a car on a racetrack or a satellite orbiting the Earth? Let me ask you a question that sounds like a total trick. Imagine you're in a car, taking a long, circular off-ramp. Your speedometer is locked. It's not changing at all. Let's say it's steady at 60 kilometers per hour. So my question is, are you accelerating?
The answer is a huge yes. And this is where really understanding vectors pays off. Remember, velocity isn't just speed. It's speed times direction. Even if your speed is constant, your direction is constantly changing as you go around that curve. And any change in velocity, whether it's speed or direction, is, by definition, an acceleration.
We have a name for this. It's called centripetal acceleration. It literally means center seeking. And that's exactly what it does. To make anything turn in a circle, there has to be some kind of acceleration that's always pulling it toward the center of that circle. This is the invisible string that keeps a satellite from flying off into deep space. And this explains a feeling we've all had. You know why a really tight turn feels so much more intense than a big, wide, sweeping one? It's right here in the math. The acceleration you need goes up with the square of your speed, so doubling your speed quadruples the pull. But a bigger radius makes it feel gentler. It's the physics behind what keeps your car on the road.
So think about it. From a penguin's jump, to a pilot's flight path, to a planet's orbit around the sun, it all comes back to one core idea. A simple but really powerful way of seeing the world, not just with numbers, but with numbers that have a direction. What is this single secret language that lets us describe and predict it all? It's the language of vectors.